Hi, my name is Lukasz, and I will speak about performance optimization and profiling. As an examples, I will use comparison of Pythonic code and patterns inherited from other languages like C, C++, or Java. And who have ever used any profiling tool on your code? Okay, and who is using these profiling tools frequently, like on daily basis? Okay, not much. Okay, so let me introduce myself a bit. I'm working as a senior Python developer at SDX Next. It's a Python software house located in Poland. I have also gave my talks at PYCON this year. This is a Python conference taking place in San Sebastian in Spain. And I was also presented at a local Python meetup, Pyra in Poznań in Poland. But what's most relevant to the topic I'm going to talk about today is that I'm really interested in performance optimization, and I'm fascinated in it. Let's now check up the agenda. I will first introduce you shortly to the performance aspects. Then we would have a live demo. Probably that would be not as effective as my musical predecessor, Ryan, but I will do my best. After that, I will summarize the talk shortly, and at the end, we would hopefully have some time for questions. Okay, so introduction. What are the base aspects of performance? First of all, it's CPU. We all want our code to be as fast as possible. That's also what our client and our end user cares about most. Google statistic says that more than the half user will abandon the website if it takes more than 3 seconds to load. And moreover, each single second causes the customer satisfaction to drop by around 15% and conversion to drop by 5 to 10%. Another thing is memory. The truth is that we don't care about it until we run out of memory, and I must admit it's a fair approach. Why should we be worried about it if there are no side effects of it? But we should still be aware of any memory leaks, because this may affect our software in the way we cannot predict. Remember that you don't have such fixtures in testing environment that then will be used in production. So the scale of the memory leak may cause serious issues here. And the last factor is input-output operations, for example, database operations. This may massively influence the main point, so the CPU time, so the time of our code. But there is also another side effect. Some services like Google App Engine provide resources like databases up to certain quota. So each read and write to the database over that limit will cost us real money. What should we do to optimize our code in the good way? So first we have to plan and predict which approach, which implementation and data structure will be the best in our case. But that's not all. Then we should profile our code. It would be good to provide a few proof of concepts with fake data, just to indicate which one is better. But once we ship our code, we should monitor performance in a living ecosystem. Keep in mind that you will never be able to test each set of data, and you can be almost sure that your end user will discover some edge case which may also relate to the technology stack he's using. Once we have that benchmarks collected, we can identify bottlenecks and quick wins. And at the end, we should optimize it all, but there's exception here. We shouldn't really spend 2 weeks on optimizing some code to get 1% of gain. We should always try to find something we can fix at low cost, but something that will maximize our profit. There are many profiling tools available in PyPI. I will just introduce a few of them, which I will use during the demo. So cprofile is the first library. It's to inspect CPU usage on specific functions. This is part of standard library, and that's the most accurate tool from available. Next one is memory profiler. This is a third-party library available on PyPy. It's better than other options, but it's still not perfect. Results may vary a bit from the reality. We just need to remember that these are just profiling tools and will not give us an exact results. PSUtil, that's a third-party library. It's plugin backend for memory profiler, which can work without it, but will be massively slow without PSUtil. Last tool I will use is this. It's a built-in library. It's used to disassemble the code so you can inspect it at a lower level. Okay, demo part. I have set up a separate virtual machine with one core on Ubuntu with Python 3.6, and I will use it for examples. Okay, so first, how we do profiling using CPU profile and memory profiler. So here you can see two functions. First one will just generate random strings, and we will profile this one using cprofile. And the second one, which is first creating the list, then it's deleting it's creating second list, and it's then deleting the first one and returning the second one. We will profile this from memory point of view, and we can do it using decorator profile. We can pass precision, so we will have memory displayed with specific digits after the comma. Okay, so let's run it. Here we can see output from cprofile. It displays how many function calls it takes at the top, and there is overall time also at the top. Then we have a breakdown by specific functions. with its time per call and total time. As you could see, memory profiler is running very slow. It's even slower without PS utils, as I mentioned. And here we can see that we can see the code over here, and we see the first column shows us overall memory usage. That's the memory taken by process. Second column shows us the increment of memory. So we can see that here we create the list A, then list B, which takes around 4 megabytes. And then when we deleting list A, we see that less space has been freed than when it was created. So we created 4.16 megabytes of data and deleted 3.5. Okay. Another thing I want to point is that when we profile, we should take into consideration deviations. So I will run first example here, so just list comprehension with simple multiplication. I will run it 3 times. We can observe that times are slightly different. These are not great deviations, but we should be aware that we will have some deviations, and we should not trust 100% this tool, or just call it few times to be sure that this specific function is running too long. And memory profiler is still running the third one. Yeah, and we can see that increment here is different on the same code, which might be weird for you. And it was also weird for me when I created this demo, and I just figured out that the amount of memory in the process is still the same in all examples. And as I mentioned, memory profiler is not perfect. Okay, so now let's compare 3 ways to create a list. So first is list comprehension, second one is creating the list and appending results to this list. It's a known pattern from other languages like C, C++. Then, as the last example, extend. So first creating the empty list and extending it with generator. Okay, so we can see list comprehension is definitely fastest. Then we have extend, and then there is traditional approach with appending. So if we can just use the list comprehensions, another option if you, for example, need to append some multiple results, just use extend where it's applicable. Memory profiling is still running. However, there should not be any differences. And again, we're looking at these values for process and not increments, as these may be not accurate. Yeah, extend is still running. Yeah, finished. So we can see that it's taking exactly the same amount of memory. Second example is comparison of data structures. So first we have tuple, then list, then set, and dictionary. So first we have time benchmarks. So list is the fastest one, created with list comprehension. Then we have set, and tuple is definitely slowest. There is also dictionary, but dictionary is a bit more complex than these three base structures. From memory point of view, there will be no difference with memory profiler. Sorry, actually, the dictionary will return a lot more memory than tuples, lists, and sets. I will just comment this one and focus on size of these objects. So we can see here that tuple is definitely smallest. Then we have list. Then sets are 4 times larger than tuples and lists. And then we have dictionary, but obviously it keeps much more data than just tuples, lists, and sets. So my thought here is that we should always use tuple unless we need it to be mutable, then we should use lists. Another example is the copying of the list. So first one is using the list constructor, then we use list comprehension, then we use slicing, so the empty slice which will return the exact copy of the list from the start to the end. Then we use built-in library copy with copy and deep copy functions. Deep copy is still running, however, some of this has already finished. So we can see that slicing is the fastest method to copy the list. Then we have the built-in copy method. Then we have list comprehension and list constructor. And at the very end, we would have deep copy, which took a lot longer than the previous cases. Now we have an example of using in operator, actually keyword. So in Python you can use in, and there is another example taken from C. So you iterate over the whole list and then compare each element of this list to the one you want to find, then you break. So I consider 2 cases. First one is positive match, and second one is the negative match, so the element we're looking for is not contained in the list. So here we have the Python in operator in positive case, and the case with the C concept of finding element. It's less slower, but when I ran it previously, it was 2 times slower. So you can see now that the profiling has different deviations. And negative case, we can see that it's 2 times slower than positive match, both in Python and for loop approach. Another known construct from languages like C, C++ is taking elements of the list by index. In Python we can do that easier within the zip function and or just with dictionary. Let's see which one would be the best in this case. So we can see that zip is the fastest one. Then we have dictionaries, and then elements taken by index. Another nice feature of Python is using slots. When you define slots on the object, Python will just allocate the X property on this object and will not allow you to define another properties in runtime, which is which may stop you from doing some things, but this way you can get more optimized performance. And here we create the lists of these objects without slots and with slots. So we can see that with slots it runs a bit faster, and from memory point of view we can see that it consumes around 17.5 megabytes and 3 times less when we use slots, actually. Another example is copying objects. I also taken 2 examples here, so class without slots and class with slots. I will just run it, and as this will long for a few minutes. Yeah, and we're creating objects like this. So we create my class, then to property x of this class we assign another object of my class, and then we assign plain object to attribute x here. So first we will just create objects without slots and with slots. Then we will use copy on these objects, and then we will use deep copy on these objects. Difference between copy and deep copy is that copy just copies the top level element and does not go deeper, so it just keeps the references to the attributes in the top level objects. So it does not get copy of the low level elements. Like here, just my class will be copied, and then these 2 objects will be just referenced in the new one. Okay, so from the time perspective, slots are running faster, obviously, and then we have a copy method, which is taking 1.8 seconds, and deep copy, which is taking 13 seconds. It's much slower, but as I mentioned, the copy will not copy the objects on the lower level, which we can observe here with memory profiler. We can see that copy takes just 5 megabytes here, and here we have full objects copied with a deep copy which takes 2 times much memory. Another example is I ran out of time a bit, unfortunately. Okay, let's summarize it shortly. So, first, we should predict what can be the best solution based on our experience, on the examples you just saw, or just based on your hunch. But predict is not the final solution. This may be misleading. We should not trust our presumptions and always profile our code, even if we think it's fastest or fast enough, just check it. And last thing, predict return on investment. Try to find the best ratio between possible profit and optimization cost. There is no point in spending weeks on optimization, which will give us unnoticeable improvement. Thank you for your attention. You can see here the two links with QR codes. The one on the left links to slides with examples from the demo, and the second one on the right is a feedback form. I would like to ask you to give me a feedback on my talk, so I can improve myself in the future and give better talks for you. You can of course catch me later during the conference. You can email me and also find me on Slack. Thanks.